In the last video, we talked about the recommender system problem, where, for example, you may have a set of movies and you may have a set of users, each of whom has rated some subset of the movies. They've rated the movies 1 to 5 stars or 0 to 5 stars. And what we would like to do is look at these users and predict how they would have rated other movies that they have not yet rated. In this video, I'd like to talk about our first approach to building a recommender system. This approach is called content-based recommendations. Here's our data set from before, and just to remind you of a bit of notation, I was using NU to denote the number of users, and so that's equal to 4, and NM to denote the number of movies. I have 5 movies. So how do I predict what these missing values would be? Let's suppose that for each of these movies, I have a set of features for them. In particular, let's say that for each of the movies, I have 2 features, which I'm going to denote X1 and X2, where X1 measures the degree to which a movie is a romantic movie, and X2 measures the degree to which a movie is an action movie. So if you take a movie, Love That Lasts, it's 0.9 rating on the romance scale. So it's a highly romantic movie, but 0 on the action scale. So almost no action in that movie. Romance Forever, so 1.0, a lot of romance, and 0.01 action. I don't know, maybe there's a minor car crash in that movie or something, so it's a little bit of action. Skipping one, let's do Swords versus Karate. Maybe that has a 0 romance rating, no romance at all in that, but plenty of action. And non-stop car chases, maybe again there's a tiny bit of romance in that movie, but mainly action. And Cute Puppies of Love, again, mainly a romance movie with no action at all. So if we have features like these, then each movie can be represented with a feature vector. Let's take movie 1, so let's call these movies, movies 1, 2, 3, 4, and 5. But my first movie, Love At Last, I have my 2 features, 0.9 and 0. And so these are features X1 and X2. And let's add an extra feature as usual, which is my intercept term feature X0, which is equal to 1. And so putting these together, I would then have a feature X1. The superscript 1 denotes is the feature vector for my first movie. And this feature vector is equal to 1. The first 1 there is this intercept term. And then my 2 features 0.9, 0, like so. So for Love At Last, I would have a feature vector X1. For the movie Romance Forever, I may have a separate feature vector X2, and so on. And for Swords versus Karate, I would have a different feature vector X superscript 5. Also, consistent with our earlier notation that we were using, we're going to set n to be the number of features not counting this X0 intercept term, and so n is equal to 2 because we have 2 features, X1 and X2, capturing the degree of romance and the degree of action in each movie. Now, in order to make predictions, here's one thing we could do, which is that we could treat predicting the ratings of each user as a separate linear regression problem. So specifically, let's say that for each user j, we're going to learn a parameter vector theta j, which would be in R3 in this case. More generally, theta j would be in Rn plus 1, where n is the number of features, not counting the intercept term. And we're going to predict user j as rating movie I with just the inner product between the parameters vector theta and the features xi. So let's take a specific example. Let's take user 1. So that would be Alice, and associated with Alice would be some parameter vector theta 1. And our second user, Bob, will be associated with a different parameter vector theta 2. Carol will be associated with a different parameter vector theta 3, and Dave a different parameter vector theta 4. So let's say we want to make a prediction for what Alice will think of the movie Cute Puppies of Love. Well, that movie is going to have some parameter vector x3, where we have that x3 is going to be equal to 1, which is my intercept term, and then 0.99, and then 0. And let's say for this example, let's say that we've somehow already gotten a parameter vector theta 1 for Alice. We'll say later exactly how we come up with this parameter vector. But let's just say for now that some unspecified learning algorithm has learned the parameter vector theta 1 and is equal to the 0, 5, 0. So our prediction for this entry is going to be equal to theta 1, that is Alice's parameter vector, transpose x3, that is the feature vector for the Cute Puppies of Love movie number 3. And so the inner product between these two vectors is going to be, 5 times 0.99, which is equal to 4.95. And so my prediction for this value over here is going to be 4.95. And maybe that seems like a reasonable value if indeed this is my parameter vector theta 1. So all we're doing here is we're applying a different copy of essentially linear regression for each user, and we're saying that what Alice does is Alice has some parameter vector theta 1 that she uses, that we use to predict her ratings as a function of how romantic and how action-packed a movie is, and Bob and Carol and Dave, each of them have a different linear function of the romanticness and actionness, or degree of romance and the degree of action in a movie, and that's how we're going to predict their star ratings. More formally, here's how we can write down the problem. Our notation is that Rij is equal to 1 if user j has rated movie I, and Yij is the rating of that movie if that rating exists. That is, if that user has actually rated that movie. And on the previous slide, we also defined these theta j, which is a parameter for each user, xi, which is a feature vector for a specific movie, and for each user and each movie, we predict that rating as follows. So let me just temporarily introduce one extra bit of notation, mj. We're going to use mj to denote the number of users rated by movie j. I'm going to need this notation only for this slide. Now, in order to learn the parameter vector for theta j, well, how can we do so? This is basically a linear regression problem. So what we can do is just choose a parameter vector theta j so that the predicted values here are as close as possible to the values that we observed in our training set, to the values we observed in our data. So let's write that down. In order to learn the parameter vector theta j, let's minimize over my parameter vector theta j of sum, and I want to sum over all movies that user j has rated. So we write this as sum over all values of I, that's a colon, Rij equals 1. So the way to read this summation index is, this is summation over all the values of I so that Rij is equal to 1. So this is really summing over all the movies that user j has rated. And then I'm going to compute theta j transpose xi. So that's the prediction of user j's rating on movie I, minus Yij, so that's the actual observed rating, squared. And then let me just divide by the number of movies that user j has actually rated. So let's divide by 1/2 mj. And so this is just like the least squares regressions. It's just like linear regression, where we want to choose the parameter vector theta j to minimize this type of squared error term. And if we want, we can also add in a regularization term, so it's a plus lambda over 2m, and this is really 2mj, because it's as if we have mj examples, right? Because if user j has rated that many movies, it's sort of like we have that many data points with which to fit the parameters theta j. And then let me add in my usual regularization term here of theta j k squared. As usual, this sum is from k equals 1 through n. So here, theta j is going to be an n plus 1 dimensional vector, where in our earlier example n was equal to 2, but more generally, n is the number of features we have per movie. And so as usual, we don't regularize over theta 0. We don't regularize over the bias terms. Those sums from k equals 1 through n. So if you minimize this as a function of theta j, you get a good solution. You get a pretty good estimate of a parameter vector theta j with which to make predictions for user j's movie ratings. For recommender systems, I'm going to change this notation a little bit. So to simplify the subsequent math, I'm actually going to get rid of this term mj. So that's just a constant, right? So I can delete it without changing the value of theta j that I get out of this optimization. So if you imagine taking this whole equation, taking this whole expression and multiplying it by mj and get rid of that constant, and when I minimize this, I should still get the same value of theta j as before. So just to repeat what we wrote on the previous slide, here's our optimization objective. In order to learn theta j, which is the parameter for user j, we're going to minimize over theta j of this optimization objective. So this is our usual squared error term, and then this is our regularization term. Now, of course, in building a recommender system, we don't just want to learn parameters for a single user. We want to learn parameters for all of my users. So I have n subscript u users, so I want to learn all of these parameters. And so what I'm going to do is take this optimization objective and just add an extra summation there. So this expression here with the 1/2 on top, I guess, is exactly the same as what we had on top, except that now instead of just doing this for a specific user theta j, I'm going to sum my objective over all of my users and then minimize this overall optimization objective, minimize this overall cost function. And when I minimize this as a function of theta 1, theta 2 up to theta nu, I will get a separate parameter vector for each user, and I can then use that to make predictions for all of my users, for all of my n subscript u users. So putting everything together, this was our optimization objective on top, and to give this thing a name, I'm just going to call this j of theta 1 ... theta nu. So j, as usual, is my optimization objective, which I'm trying to minimize. Next, in order to actually do the minimization, if you were to derive the gradient descent updates, these are the equations that you would get. So you take theta j, k, and subtract from it alpha, which is the learning rate, times these terms over here on the right. So we have slightly different cases for when k equals 0 and when k is not equal to 0, because our regularization term here regularizes only the values of theta jk for k not equal to 0. So we don't regularize theta 0. So we have slightly different updates for k equals 0 and k not equal to 0. And this term over here, for example, is just the partial derivative with respect to your parameter, that of your optimization objective, right? And so this is just gradient descent, but and I've already computed the derivatives and plugged them into here. And if this and if these gradient descent updates look a lot like what we had for linear regression, that's because these are essentially the same as linear regression. The only minor difference is that for linear regression, we had these 1 over m terms. It's really would have been 1 over mj, but because earlier when we are deriving the optimization objective, we got rid of this. That's why we don't have this 1 over m term. But otherwise, it's really some of my training examples of the error times xk plus that regularization term, plus that term that the regularization term contributes to the derivative. And so if you're using gradient descent, here's how you can minimize the cost function j to learn all the parameters. And using these formulas for the derivatives, if you want, you can also plug them into a more advanced optimization algorithm like conjugate gradient or LBFGS or what have you, and use that to try to minimize the cost function j as well. So hopefully you now know how you can apply essentially a variation on linear regression in order to predict different movie ratings by different users. This particular algorithm is called a content-based recommendations, or a content-based approach, because we assume that we have available to us features for the different movies. And so we have features that capture what is the content of these movies, of how romantic is this movie, how much action in this movie, and we're really using features of the content of the movies to make our predictions. But for many movies, we don't actually have such features, or it may be very difficult to get such features for all of our movies, for all of whatever items we're trying to sell. And so in the next video, we'll start to talk about an approach to recommender systems that isn't content-based and does not assume that we have someone else giving us all of these features for all of the movies in our data set.